This video is for Chapter 7, number 48. So in this problem, a basketball player is trying to make a half-court shot, and he releases the ball the height of the basket. So assuming the ball is launched at 51 degrees and 14 meters from the basket, what speed must the player give the ball? So let's draw a picture here. So we've got this person shooting the ball, and the goal is at the same height. So basically, I've got a situation that looks like this. So I'm going to shoot the ball at some particular angle, and it's going to go in over here. So what do I have? I've got a 51 degrees initial angle here, and I know that I am 14 meters from the basket. So from that point to that point is 14 meters, and I want to know what is the initial velocity of the ball. So I'm looking for initial velocity. So the fact that they didn't specify a x or a y direction, they're wanting the resultant vector of the initial velocity. So they're asking for basically this particular part of the diagram. Alright, so now that we've got that, let's go ahead and split this up into our x and y directions. So we've got our x here, got our y on the other side. So things we can know for x, we can know distance in the x, we can know initial velocity in the x, and we can know time in the x. Now once again, for these problems, because my speed is not going to change in the left to right direction or the x direction, we know that initial velocity in the x is equal to the final velocity in the x is also equal to just the velocity in the x. All three of these are the same thing, so just keep that in mind. Now for the y's, we've got some other things. We can know a final velocity in the y direction. We can know an initial velocity in the y direction. We can know a distance in the y direction. We can know an acceleration in the y direction. And we can know a time in the y direction. Okay, so this is always going to be negative 9.8 because things are falling on Earth, and that is acceleration due to gravity on Earth. So negative 9.8 meters per second squared. Now remember that the variable that links these two directions together is your time. So the time something goes out is equal to the time something falls down. So Tx is equal to Ty. Okay, so now let's go ahead and see what we've got here. So what I'm going to do is I'm going to break this up in half. I'm going to go from this point up to this point. And the reason why I do that is because as we throw something up in the air, its speed will decrease because gravity is pulling down on it. So as something goes up higher, its speed gets slower and slower and slower until its speed reaches zero. At the point that the speed reaches zero, it means that it is at its highest point. So I'm going to go ahead and put in 0 meters per second for the final velocity in the y direction. And then that's basically going to let us focus on the left-hand side of this diagram. Alright, so in that case, because we're looking at half, this is going to be 7 and this is going to be 7. So we're going to say my distance in the x direction is going to be 7 because we're only going to the midpoint here. So I'm going to say 7 meters is my direction in the, or is my value in the x direction. Alright, so let's see what else would I know here. So let's go ahead, and because we know that time links one another, let's go ahead and solve. So we've got distance is equal to velocity times time. Let's solve this equation for t. If I divide this side by v, divide this side by v, I'm going to get time is equal to distance in the x direction divided by my velocity in the x direction also. And that's the x direction. So let's keep this in mind. So over here I've got final velocity, I've got acceleration. An initial velocity would be helpful. I don't know what the initial velocity is in the y direction here, but what I can do is I can write the initial velocity in the y direction in terms of the initial velocity in the x direction. So let's go down here. Let's draw this little triangle again. Okay, so if that represents my initial velocity, and this is 51 degrees, all right, so from that, and I know that this is a 90-degree angle, I know that this angle here has got to be 39 degrees, okay? So this is my resultant vector. Let's get another color here. So green, this one is going to represent my y component, and let's do red for my x component, okay? So my x component there. So I know that this angle 39, so let's say, so this was initial velocity in the x direction, and back to my green was the initial velocity in the y direction. I don't know what my initial velocity in the y direction is, but I do have a ratio here. I know that this referencing 39 degrees, the opposite is VIX and the adjacent is VIY. So if I've got the opposite and I've got the adjacent, I know that that's tangent. So I can say that the tangent of 39 is equal to my opposite side, which is VIX. So let's go to my red here. So VIX over VIY. So I know that this ratio between the initial velocity in the x divided by the initial velocity in the y is equal to the tangent of 39. And this just comes from the definition of what tangent is. Okay. So now what I can do is I can rearrange this formula to get VIY is equal to something. So if I multiply this side by VIY and multiply this side by VIY, I'm going to get VIY times tangent 39 is equal to VIX. So I'm trying to get VIY. So the next thing that I want to do here is I want to divide this side by tangent 39, and I'll divide this side by tangent 39. So then I'm going to end up with my initial velocity in the y direction is equal to my initial velocity in the x direction divided by tangent of 39. So this is what I'm going to put in place for VIY up here. So I'm going to say VIX divided by tangent 39. Now, even though I don't technically know what it is, I know this expression gives me the value for it. Alright, so the next thing that I want to do is we know that this formula, this kinematic formula, acceleration is equal to final velocity minus initial velocity divided by time. So let's go ahead and plug in what I know here. So negative 9.8 is equal to final velocity, which was 0. My initial velocity is this. So I'm going to say initial velocity in the x direction, excuse me, divided by my tangent 39. Now this just takes the place of my VI, and then I'm going to divide the whole thing by my time. So I don't have time, but I'm going to put time down there. Okay. So now, if I know that this expression is equal to time in the x, well now let's go ahead and solve this expression for time. So if I multiply this side by t, multiply this side by t, I'll get negative 9.8t is equal to negative VIX divided by tangent of 39. But then if I take this, divide by negative 9.8, and then divide this side by negative 9.8, I'm going to get time is equal to negative VIX divided by tangent 39 divided by negative 9.8. So that's what my time is equal. Well, I know if time is equal to this expression and time is equal to this expression, time is equal to this expression here, time is equal to this expression here, I can set these two equal to one another. So let's get a different color here. So let's do that. So we're going to say, let's see what color I got. Let's do blue. So I'm going to say my distance in the x direction, which was 7. So I'm going to say, well, let's just do this. Let's write it out first. Distance in the x direction divided by velocity in the x direction is equal to what I have in the circle over on this side. It's going to be negative VIX over tangent 39 divided by negative 9.8. So this is advantageous because I've only got, well, it will be. I only have two variables here. I've only got VI or my VX. Now remember we said that VIX is the same thing as VX. So these two variables are basically the same thing. So I did have a distance in the x direction. So let's go ahead and plug that in. So now I'm going to have 7 over velocity in the x direction is equal to negative velocity in the x direction divided by the tangent of 39 all over negative 9.8. Okay, so when I solve this, if I solve this equation for Vx, now I'm skipping a bunch of steps here, but number one, I'm kind of running out of room, and number two, this is just algebra here, solving this equation for Vx. So once you solve this equation for Vx, you're going to get Vx is equal to 7.45 meters per second. So that's going to be your initial velocity in the x direction. So going back to here, this Vix here is going to be 7.45 meters per second. Well, now, if we're looking for the initial velocity, we're looking for the resultant vector, which is going to be this blue one. Well, here I've got an angle, which is 39, and I've got one side, which is 7.45. So now if I can just solve for the resulting vector, let me draw another triangle up here and put that stuff in. So I've got this. I know this angle is 39, and I know that this side here on top is going to be 7.45, and I'm basically going to solve for here, my resulting vector. So here I've got an angle, which is 39 degrees. So I've got my opposite over hypotenuse. So opposite over hypotenuse is going to be sine. So I'm going to say sine of 39 is equal to my opposite, which is going to be 7.45 over my r. Okay, so if I multiply each side by r, multiply this side by r and this side by r, I'm going to get r sine 39 is equal to 7.45. And if I divide this side by sine of 39, divide this side by sine of 39, I'm going to get r is equal to 11.84 meters per second. And that is going to be your final answer. That is going to be the initial velocity. This is your blue velocity. So that is your overall resultant velocity. Your initial, your x velocity we calculated somewhere. What was it? Yeah, your 7.45. Now we could calculate this. It didn't particularly ask for the VIY, but we could calculate it. But anyhow, notice that the resultant vector is always bigger. The resultant vector is always bigger than the components that make it up, which makes sense because the hypotenuse is always going to be the longest side of the longest side of a triangle. So hopefully that helps.